Hello students, today we will discuss about the uh, storage virtualization technology called as RAID and different levels of RAID. So last session we were discussing about storage virtualization, which are dealing with how we are internally managing the placement of different disk arrays, how it is being separated from the user, and how this virtualization can be provided. So RAID is a standard that is used for providing this uh, storage virtualization. A RAID actually means a redundant array of inexpensive disk. Redundant array of inexpensive disk, or it is also called as redundant array of independent disk. So in both ways we are calling this as RAID, redundant array of inexpensive disk or redundant array of independent disk. So it is a technology that combines multiple physical disk drive components into one or more logical units. So this is the procedure that is happening with the RAID, means the disk array technology. So by providing different data redundancy or similar features, the user is getting the data always without having any confusion. So we are using different levels. We are using different levels of RAID through which we can maintain the disk and we can store the data in that based on the different levels available. So before moving into the discussion on different levels of RAIDs, we will discuss about the different basics, the basic terms related to the levels of RAID. So RAID levels are defined based on the following three concepts. One is called as stripping, the second one is called as mirroring, and the third one is called as parity checks. So based on these three, we are maintaining the different levels of RAID standards. So what is this stripping, what is this mirroring, and what is this parity check, we will see in our following slides. Now first we will see about stripping. So a RAID set, so RAID is actually a concept that is being provided for maintaining a group of disk together as a disk array. So a RAID set is a group of disk, and so we'll be having number of disk available, and within each disk a predefined number of contiguously addressable disk blocks are defined, which are called as strips. So with each disk some contiguous addressable block are being defined. Okay, so this can be called as a strip, and for another disk also we are forming similar contiguous addressable disk, which can be called as a strip. So with each disk some location, some contiguously addressable. Contiguously addressable means one address after another address. In that format, some continuous locations are being collected together to form a single strip. So we'll be doing stripping, and based on these different strips, on these different strips we are placing the data. So the set of aligned strips that spans across all the disk, the set of aligned strips, so similar strips that are aligned across all the disk. So this is one disk, this is another disk, and the alignment of these different strips together with some continuous addressable blocks are forming a stripe. So then it can be called as a stripe when several disks are connected. So when we are having number of disk arrays available, so different disks will be there, and each disk will be having strips available, and if these strips are aligned in the same way, it can be called as a stripe. We will see that in our example diagram. We will see that. And the strip size, which is also called as stripe depth, strip size. So this is one strip, this is another strip. Similarly, a number of strips will be available, Strip size means the total number of strip, that is the indication here, the total number of strip, or which is also called as stripe depth. So stripe depth defines the depth, how many strips are available, that defines the stripe depth, the total depth of a stripe that is formed by connecting different strips. That describes the number of blocks present in a strip, that describes the number of blocks present in a strip. Okay, so it is the maximum amount of data that can be written to or read from a single hard disk drive. It is the maximum amount of data that can be written to or read from a single hard disk drive at a time in the set before the next access. So at a particular time, the data can be accessible from any of these strip. It is part of the entire drive. Now when the next access arrives, it can be accessed from the next strip. Okay, assuming that the access data starts at the beginning of the strip. So access data start from here, end at here. So similarly, at a time with the other also, it can have access to the same strip. So the maximum amount of data that can be written to or read from a single hard disk drive in the set before the next hard disk is accessed is actually the entire strip or strip size. So you'll see the pictorial representation of that. So here you can see these are some disk that are connected, so disk arrays. So this forms the strip. So the same strip size here, same strip size here. Similarly for this also, strips are there, strip size are there, so that defines the depth of the strip. Okay, so similarly, so these are association, different disks are one after another, these disks are connected. So similarly, so this is one hard disk, this is another hard disk, this is another hard disk, will be having a number of disk arrays present. So this is the one basis for defining the different RAID levels. So the levels that are defined based on strip. So first basis is the stripping. Stripping is the division of each disk into some continuous addressable blocks that is common for all the disks that are part of the disk array. Now second concept is second base for the RAID level. Defining the RAID level is based on mirroring. So what do you mean by mirroring? Mirroring, as the name indicates, something that is being imitated or repeated. It is a technique whereby data is stored in two different hard disk drives. Same data like X is there in this disk as well as in this disk. Same data is mirroring on the second disk also. So that is the term mirroring. So data is stored on two different hard disk drives. That means it will be having two copies of the same data. Now if one hard disk fails, it can have access to the same data from the second drive. That is the main advantage of using mirroring. And the controller will continue its service, that data request, if one is missing, it can be taken from the mirrored pair, that is from the second hard disk drive. When the failed disk is replaced, so if this is under failure, it will access to this one. If the failed disk is replaced with a new disk, the controller copies the data from the surviving disk of the mirrored pair. So the data will be copied into this drive again. So that is the procedure. So while doing storage virtualization, it is following this concept. So if this disk goes under failure, control goes to this one. Then after some time, this disk will be replaced. Automatically this data will be copied back to the initial drive. So this activity is transparent to the host, which is not known to the host, which are actually communicated with the storage device. So in addition to providing complete data redundancy, mirroring enables faster recovery from disk failure. However, disk mirroring provides only data protection and is not a substitute for data backup. So it is actually a mechanism for data protection, because we need to maintain the same data again. It is not like a substitute for the data that is required for our application. Now mirroring normally captures changes in the data, whereas a backup captures point in time images of data. So there is a difference between mirroring and backup. Backup is different actually. Mirroring is only maintaining the data. If it is not available, the task is given to some other, but later it will be coming back to the same device itself. Backup is different. That is like storing each status on the second device. It is not like backup concept. Now mirroring involves duplication of data. Of course that will be happening. That is, the amount of storage capacity needed is twice. So that will be the drawback of using mirroring, and the amount of data being stored is actually is more. So mirroring is considered expensive. Of course it is clear, and is preferred for mission critical applications. So this concept, this type of level, rate levels that depends on mirroring is applicable for only some critical situations, and where the data cannot be lost in any moment. So it improves read performance, because read requests can be serviced by both disks. So if a data is required at a particular time, if it is not available, so read is always possible from any of the disk, or either from the original disk or from the mirroring disk. So write performance will be affected, because each write will need to write into the initial as well as to the mirror, that is a second disk also. So reading is also, it is okay, but writing, if something is written here, that is to be written here also. So writing task is more. Two writes are actually required for if it is being mirrored two times. Now the third point related to the RAID level is the parity. Third basis for defining RAID is parity. So parity is a method of protecting the data stored in the strip. That is the protection of data when the hard disk drive is a failure, if it is getting a failure, without the cost of mirroring. So some parity must be maintained to store or retrieve the data that is being lost during the failure of the hard disk drive. So an additional hard disk drive is added to the strip width to hold parity. So normally one additional hard disk drive is maintained to store the parity information, and by using a mathematical construct that is used for the recreation of the missing data. If some data is being missed, so it can go to the hard disk drive where the parity information is stored, and by applying some mathematical construct, we can retrieve the data that is being lost. So parity is a redundancy check that ensures full protection of data without maintaining a full set of duplicates. So parity is a solution without having mirroring. Without using mirroring concept, we can retrieve the data that is being lost. And the parity information can be stored on separate hard disk drive, or it can be stored on distributed among different drives. Sometimes it can be stored as a separate hard disk drive, or it can be distributed over different hard disk drive connected to the RAID set. So the three bases for forming the RAID standard is stripping, mirroring, and parity. So the storage of parity means normal case, this is one disk array, second disk array, third disk array, fourth disk array, and this is used as a disk array which is exclusively used for storing the parity disk. So all these are data disk, and this is a parity disk. So parity disk is stored separately, which can be used for retrieving the data that is being lost based on the parity value. So we need to maintain some information frequently as part of this parity disk. Now we will see about different RAID levels. first level, that is called as RAID 0. So we will see the structure of each of these RAID levels. So RAID 0, the concept is actually like the data is stripped across the hard disk drive. Data is stripped across the hard disk. So in this mechanism, RAID 0, it actually utilizes the entire storage capacity by distributing the strips of each disk over multiple hard disk drive in the RAID set. So the strips of each hard disk drive will be distributed over multiple hard disk drive. That means the entire storage capacity is deal with the different strips associated with all the hard disk drive. So when we try to read data, all the strips are put back together by the controller. So the same strips are being referred together when we want to access the data together. The same strips are being taken under consideration for the access to a particular data. Now the stripe size is specified in the host level for the software used for RAID, and it is vendor specific for hardware RAID. So the software associated with the RAID will be depending on the vendor who is trying to access that particular data. When the number of drives, so a number of hard disk drives are available and the data are stripped across different drives. So the data are stripped, that means the partitions are distributed among different disk drives and they are being accessed by using a common controller. So when the number of drives in the array increases, performance improves because more data can be taken, read, or more data can be written into the disk simultaneously because the strips are associated with more number of hard disk drives. And this RAID 0 is used in the applications that require more I/O operations. That means where we require a high speed input output throughput, more data to be read, more data to be written. That situation we are using because the data is distributed among different hard disk drive. But these applications require high availability because the data must be always available. As it is always require high availability, it does not provide data protection. So the data protection is not supported by RAID 0, and availability in the event of drive also because of failures we cannot protect the data that is present with this usage of RAID 0 standard. So the main point to be considered in RAID 0 is the data is stripped across various hard disk drives. So we know what is stripping because some contiguous memory location the data is being stored and it is being distributed among different disk drives in the disk array. So data will be accessed through only those stripe, and every time the data can be, so whenever we need to write some data, access to that particular strip. Whenever we need to read some data, access that particular strip. That is the procedure that we are following in RAID 0 disk array. So this is the first category. So we'll see the pictorial representation of RAID 0 architecture. So these are the data that is given from the host, that is A, B, C, D, E. 5 data are being given. So this is the RAID controller. So for every RAID standard there will be a controller who controls the access to the various disk drives that are connected as part of the disk array. So these 5 datas. So once again look carefully on the working of RAID 0. So this 5 data, A is the data. One portion of data A is placed in the first disk array. A portion of A is that is stored in the second disk array. Portion of A is stored in A3, A4 and A5. So the data is distributed among different disk drives. So some portion of B is also distributed among different disk Similarly for C, for D and for E. We can see that it is following stripping. That means the portion of data are distributed among different disk drives. So this disk 1, 2, 3, 4, 5 disks are available in the first disk array, and in the first disk some portion of A is being stored. In the second, some portion of B is being stored. Similarly, the remaining portions of all other. So next disk array, some portion of first element A. Similarly for B, C, D, E. Similarly for all other disk arrays, we are having these stripes are being stored separately. But we can see that there is no mirroring. There is no. So here we are only following stripping. There is no mirroring. No data is being repeated. And also we can see that there is no importance given to parity. There is no areas where we are providing any parity information. So RAID 0 is entirely focusing on the stripping concept. The data is distributed among different disks. Now we will move to the next level, that is RAID 1. RAID 1 is actually based on mirroring. So data is mirrored to improve the fault tolerance. Means if some data is missing, we need to access that data based on the mirroring concept. So as we know, mirroring means the same data will be replicated on some other drive also. So a RAID 1 group consists of at least 2 hard disk drive. At least there must be 2 hard disk drive, so that we can repeat the element one more time. So every write is written to not only to a single disk, it is written into a second disk also, so that the data will be redundantly available, or that is available repeatedly. So and this is transparent to the host in the hardware RAID, so which is not aware of the user whether it is having more than one copy available, but it is actually available within this standard. So in the event of a disk failure, if one disk fail, the impact on data recovery is the least among all RAID implementations, because we can access the data from the second disk. Because of this mirroring property, the data can be recovered and the operations can be continued. Okay, so the RAID 1 follows mirroring by keeping a duplicate or secondary copy of the same data once again. It is suitable for applications that require high availability. Always when the data is a must, that situation we can utilize the concept of RAID 1 configuration. So this is the example. So data, all the datas are being passed to the different number of disk that is available. So there will always be a RAID controller. Now you can see that this is one disk where we are storing A, B, C, D, E, all the elements, and its mirror set is also available, A, B, C, D, E. So A is repeated, B is repeated, C is repeated, D is repeated, and E is also repeated. So this is the data and this is the mirrored data. So the exact copy is again available within this second disk drive also. The remaining data FGHIJ, this is the real data that is stored in one set of disk array, and this is the mirrored data that is available within the mirror set, that is the second disk drive. So for every set of disk values, we will be having a mirror data also available, so that if this drive is under failure, A cannot be accessible, it can be accessible through the next hard disk drive. Similarly, if H is not available here, it can be accessible from the next mirror set available as part of the next hard disk drive. So high availability data will be always available in the case of RAID 1 configuration, but in the case of RAID 0 configuration, data availability is not given any importance, but data is distributed among different disk drive. Data portions are being distributed among different stripes, but we cannot always assure that we will always get the data if one data is one drive is having any failure. Some portion will be missing in the case of RAID 0 architecture. Now next configuration, next level of RAID is RAID 2, which is a very rarely used configuration. It stripes data at the bit level. So in the previous RAID 0, some portions of data are being distributed among different strips of different disk drive, but here the distribution is actually based on bit level, bit by bit. Each bit will be distributed among different disk drive, and it also uses the Hamming code for error correction. It is using an algorithm called as Hamming code mechanism for correcting the error because of any failure related to the data access. So the disks are synchronized by the controller to spin at the same angular orientation, so it will be rotating always. So it generally cannot service multiple requests simultaneously. So we cannot provide multiple requests simultaneously in the case of RAID 2 architecture. And also extremely high data transfer rates are possible in the case of RAID 2 architecture. So multiple requests is not possible simultaneously, but for transferring huge amount of data we can utilize the RAID 2 architecture. Now the complexity of an external Hamming code offered a little advantage only. So so we are using a Hamming code for for some additional advantage, but it is only providing only little advantage. So that is the reason why RAID 2 is very rarely being implemented. So the difference between RAID 0 and RAID 2 is RAID 0 data is being divided and they are being stripped, but in the case of RAID 2 the strips are at bit level. Bits are being distributed among different disk drive. That is the basic difference between RAID 0 and RAID 2, and RAID 2 also supports Hamming code for error correction purpose. So here you can see this is the disk 0 RAID 2 1 architecture, A1 B1 C1 D1. Here the difference is the diagram is very simple. A1 is actually a bit, a portion of element A. Similarly A2 is a bit of A2, means element A. A3 is a bit of element A. A4 is a bit of element A. Similarly, so each of these it is similar to RAID 0, but the difference is these stripes are bit level. Bits are being, so each bits are stored separately, and also we can see that we are having additional parity Hamming code disk data also available. That is this is the some portion of A, parity 1 strip is available, parity 2 and parity 3. Similarly for, so here also we can see that we require more disk for storing the parity information, also for controlling the various access of all these elements. So 2 points to be remembered. One point is each of these strips are bit level, bit by bit storage. Second thing is it requires additional disk for storing parity or the informations related to the parity data. Now we will move to the next level, that is called as RAID 3. So it also stripes data for high performance and it uses parity for improved fault tolerance. So rather than using mirroring was the method used for fault tolerance in the RAID 1 architecture, but RAID 3 follows a parity storage. Parity information is also being stored for providing a high performance, and the parity information is stored separately on a dedicated drive. So one drive is exclusively used for storing the parity information that can be used for the reconstruction of the data if the data cannot be accessible directly or if any failure happens. Now this standard always reads and writes complete strips of data across all disks as the drives operate in parallel. It also reads and writes all the stripes parallelly and it can access from all the disks simultaneously at the same time. and there is no partial writes that update one out of many stripes in the stripe. There is no partial writes, it will be always writing the data completely at every operation. It is not doing any partial operation. So RAID 3 focuses on adding an extra disk drive for storing the parity information. So this is the example. This is the host that provides the data. ABCD data is being provided, a RAID controller. So here you can see that this is exactly similar to the RAID 0. Portions of each of the elements are stored as stripes in each of the disk drive. Plus additionally we are having a parity disk, an exclusive disk drive that is used to store the parity information of each of the elements. So AP represents the parity information of element A. Similarly BP, CP, DP and EP, that is the parity information. So if any of the element fails, its corresponding parity bit from the parity disk can be utilized for the access of data due to some failure. So we need to apply some additional operations on this parity data so that we can access the data which was under failure with any of these data disk. Now we will move to the fourth level, that is RAID 4. The working of RAID 4 is like it strives data for high performance, similar to the previous one, that it also uses parity for an improved fault tolerance. When we compare to RAID 3, we are having an improved version of fault tolerance mechanism that is applied to RAID 4. So data is stripped across all the disk except the parity disk in the array. So the data is stripped across all the disk except the parity disk in the array. So the parity disk is separately maintained. The parity information is stored on a dedicated disk as in the previous, so that the data can be rebuilt if a drive fails. You will see the structural difference when we look into the diagram. And the stripping is done in block level, not in bit level. So one of the previous RAID level was following bit level, but here it is following block level stripping. Unlike RAID 3, data disk in RAID 4 can be accessed independently, so that specific data elements can be read or written on single disk without read or write on the entire strip. So individual strip can also be written or can be read on a single disk in the case of the RAID 4 architecture. So here you can see it is block level distribution on each of the disk, and finally we are having a parity disk available separately. So RAID 3 and RAID 4 also follows almost the same structure. Data is stripped across all the disks except the parity disk in the array. Parity disk is separately done. So difference between the previous one and this one is parity information is stored in a separate disk, especially so that the data can be rebuilt if the drive goes under fail, and the stripping is done at the block level. So of course in the RAID 3 the information is stored in bit level, so that will be the difference with the RAID 4 architecture. Here the data is stored in block level. So the architecture seems to be almost similar. RAID 4 almost similar to RAID 3. All this data stripping is done in block level, and parity disk is also maintained separately. Now we will look into the RAID 5 architecture. It is a very versatile RAID implementation. It is similar to RAID 4. It is almost similar to the previous case, but it uses stripping, and the strips are independently accessible. So not like the previous case where we can access all the strips together. Here we can access individual strips independently. So RAID 4 and RAID 5, the difference is between the parity location. So where we are storing the parity information. In RAID 4, parity is written to a dedicated drive. Separate drive is there, creating all the right bottleneck for the parity disk on a single additional disk drive. In RAID 5, parity is distributed. This is the main difference between RAID 4 and RAID 5. Okay, and when we look into the diagram, we can see the difference. So RAID 3 and RAID 4 seems to be similar. RAID 3 based on bit level, RAID 4 based on block level. Now RAID 5, the parity disk is not having a separate disk drive. Parity is distributed among different disk. Okay, so we'll see. This is the data ABCD. This is the RAID controller. Now this is the first disk. It is not only a data disk, a portion of A, portion of B, portion of C, portion of D, and the parity bit associated with E is stored in this particular disk. Now here in the second disk, the parity information of D is stored. In the third disk, parity information of C is stored. In the next one, parity of B, and in the next, the parity of A is being stored. So parity bit storage is distributed among all the disks. So each disk not only consists of data, it also consists of parity information also. But in the previous case, we had a separate disk drive where we could store all the parity information. So that maintenance is different because we require additional hardware, additional drives are required, and also access to that particular drive also seems to be difficult. But in the case of this RAID controller, means this RAID architecture, the parity information is distributed among different disks where we are actually storing the data itself. Now RAID 6 is similar to RAID 5 except that it includes a second parity element. It includes a second parity element also to enable survival in the event of the failure of two disks. So it is having one more parity information, that is also, if some problem with the first parity information, it can refer to the second parity information also. So it is an enhancement of the previous RAID 5 architecture. So it distributes the parity across all the disks similar to the previous case. Only thing is it is having one more parity information associated with each disk. So you can see that the first disk, it is similar to the previous case, element of A, B, C. It is having the parity information of D and E. So additional information is also stored. If any problem with E, with the second any other disk where the parity of E available, here also we can have. So here also it is available. If some problem happens to this one, this can be used for accessing that particular data. Similarly, the second thing, you can see that the parity information of C and D is stored. Here B and C parity information is stored. Here A and B parity information is stored. Here A and E parity information is being stored. So more disk of the same data disk are deputed for storing. So one more parity information is stored with each of the disk drives, so that if one parity disk of each disk array fails, it can refer to the second disk for accessing the same or for retrieving the same element from the entire disk array. Now next is a nested RAID, that is the combination of more than one RAID configuration. That is RAID 0 and RAID 1 can be combined, or RAID 1 and RAID 0 can be combined. It can utilize the performance benefits of both RAID 0 and RAID 1. They use, so as you know, RAID 0 uses stripping and RAID 1 uses mirroring. So if we mix the both techniques into a single RAID standard, you can utilize the benefits of both of these methods. So one example is given, like here here it is using this portion is using stripping and this portion is using mirroring. Similarly here is an example where we are using stripping with the mirroring, Here also we are using mirror, means these two, this is the structure that is combined with these two architectures are actually combined. So in the step 1 it will do mirroring, in the second step it will be doing stripping, or vice versa. So there will be controller, they are communicating between each other. So these values are not clear now. So in the first case either it will be doing mirroring, and in the second case it will be doing stripping, or in the first case it will be doing stripping and in the second level it will be doing mirroring. So you can see here it is mirroring, and for each mirroring it will be doing stripping, and here you can see initially it is doing stripping and then it will be doing mirroring on each set of disk drive. So the combination of this is RAID 1 plus 0, first mirroring then stripping. This is RAID 0 plus 1, two different combinations. So RAID 0 initially stripping then mirroring. So two combinations can be utilized for implementing a nested RAID standard, so that we can utilize the advantages of both stripping and mirroring. Okay, so this is a hybrid or nested RAID where we are applying more than one RAID standards for creating a new standard by taking the advantages of all the other RAIDs. So today's session we were discussing about disk array in detail, where we are mentioning about storage virtualization, and for storage virtualization we are using different RAID standards, how we are storing the data in different means based on the concepts like stripping, mirroring and parity. And based on these concepts we are using different RAID levels starting from RAID 0 to RAID 6, and plus we are having a nested RAID also. We have seen the structure of each of RAID levels and how the data is being placed, how the element is being distributed, how the parity data is being distributed, how the mirroring is being done, and finally we have seen the nested concept, where we are combining the concept of both mirroring and stripping by combining mirroring with stripping, and combining the stripping with mirroring mechanism. So that is all about the different RAID standards, and we will see some more discussions on memory in the next lecture. Thank you.